Hello everyone. The title of this video is Rational Functions Using Arrow Notation. Alright, so each example I'm going to be doing for this video is taken directly from a free online textbook at openstax.org, and I'm in their Algebra and Trigonometry text, section 5.6, called Rational Functions, and I'm under the heading Using Arrow Notation. So each example is going to be either an example directly from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Okay, so the first thing I'm doing here that I would like to show you is example 1 from the text. So let's take a look at that. So you got some reading to do. Now I have introduced arrow notation in a previous video. This is just going into a little more detail. They give you some, this little, I would highly recommend getting to know this table here. Okay. X approaches some value from the left or from the right, approaching infinity or negative infinity, and then the outputs, f of x or y approaching infinity or negative infinity or approaching some specific value. But basically the arrow means approaching. So example 1, talking about vertical asymptotes, end behavior, lots of things to read, horizontal asymptotes. Okay, and I'll probably bring those definitions up as we go through this first example. So it says here, use arrow notation to describe the end behavior and local behavior of the function graphed here. Alright, so I'm going to draw a rough sketch on my paper of this picture here, right, and we'll talk about it. Alright, so as I said, here's a very rough sketch with just certain numbers highlighted on a piece of paper. So these red dashed lines are not technically there. Right, they're not part of the graph of the function. So I have this dashed horizontal line at y equals 4. That's alright, y equals 4 over here. And then I have a dashed vertical line at x equals 2. And then you look at the rest of the actual graph, right? The solid, it's in green, but maybe it looks black or whatever on the video. But I have a solid, all these points here belong to the graph of the function, and then down here also all these points on this part of the curve. And what you're seeing is that there's these arrows here. The graph gets closer and closer to these dashed lines called asymptotes without ever actually touching them. Alright, so as you go off to the right here, the graph is getting closer and closer to the value, y equals 4, but never actually touching it. Same thing over here. As you go off to the far left, the graph is, going up toward y equals 4, but again, never actually hitting it. So that's the end behavior, right? They ask us to describe the end behavior, and we've seen end behavior for polynomials earlier in chapter 5 of this text. But for the arrow notation. For the right end behavior, we would say what happens as x goes to infinity. Right? We say as the value of x as my input goes to positive infinity, right? Approaches infinity. There's the arrow notation. As I go to the right on the x-axis, what happens to the value of, I'm calling this function f. What happens to the value of f? What happens to the outputs? It looks like they're approaching not infinity or negative infinity, but they're approaching y as, a value of 4. So it says as x approaches infinity, f of x, right, or y, the output, approaches 4. Right, not infinity or negative infinity, but the number 4 is what the output is approaching. Same thing on the left side. As x approaches, negative infinity, that's you're going to the left forever on the x-axis. What's happening to the value of the function, the output? It looks like it's also approaching 4. Right, you're approaching, getting closer to this horizontal line at y equals 4. So f of x is also approaching 4. Right. So there's the end behavior. And what I've just described here is the definition of a horizontal asymptote. If x approaches infinity or negative infinity, and your function value approaches a finite value, right, something that's not infinity or negative infinity, like the number 4, then you would say that the function has a horizontal asymptote at that value at y equals that value, y equals 4 here. So I'll write out that right here. Right, so if as x approaches positive or negative infinity, one end or the other, or both, f of x, or the y coordinates, are approaching some number a that's not infinite, right, not infinite, then we say f has a horizontal asymptote. Y equals a. Right. So again, in this example here, they would say that this function f has a horizontal asymptote y equals 4. Alright, so that's the end behavior. What happens as x goes to infinity? What happens as x goes to negative infinity? Alright, then they also asked us about local behavior. And this is just what's happening in the interior. Are there any vertical asymptotes? As we're seeing here at x equals 2. You see this vertical dashed line that the graph is approaching, from the right side and from the left side. Right on the left side of x equals 2, the graph is going to negative infinity. It's going down forever, but never actually hitting the line x equals 2. Right, there is no point of the graph on x equals 2. X equals 2 is not part of the domain of this function. And then same thing from the right side. As x approaches 2 from the right side, the value of the function is going to positive infinity, right? It's going up forever, but still never actually hitting x equals 2. Alright, so here's what we would say about what happens at x equals 2. you do a left side and a right side. So as x approaches 2, and then if you want to say from the left, if you're on the x-axis and want to approach 2 from below or from the left, you put a little minus sign above the number 2, almost like an exponent. But this means, from the left side of x equals 2. In other words, the values of x are less than 2, right? 1, 1.9, 1.99, 1.999, right? You're lower than 2 when you see this little minus sign here. So what we're seeing is, as x approaches 2 from the left, the value of f, right, the value of the function, goes to negative infinity. You can see the graph going down forever as you approach 2 from the left. And if something like this happens, if you approach a value from either the left side or the right side, and the function's going to infinity or negative infinity, then they would say that there's a vertical asymptote at x equals 2. Right, but that's only if the graph is approaching infinity or negative infinity around some value, right, around x equals 2 or 3 or whatever. Alright, then on the right side of x equals 2, let me say, separate this. As x approaches 2, now to say from the right side or from above, plugging in values, greater than 2, you put a little plus sign up here in the superscript above 2. So this little plus sign means, from the right side, you're looking at values of x greater than 2. Well, as I approach x, or as x approaches 2 from the right side, look at what happens to the graph of the function. It's going up forever. So the value of f is approaching positive infinity. And there we go. There we go. A description of local behavior, what happens at a finite value of x. Over here we say what happens as x goes to infinity or negative infinity. Local behavior, you're saying what happens to the function as x approaches a finite value, like 2 or 5 or whatever. And again, we would say that f has a vertical asymptote. Of x equals 2. Right, and the horizontal asymptote y equals 4. Alright, and again, you can look up the definition, just look in the text. But as x approaches a finite value from either the left side or the right side, if the function's going to infinity or negative infinity on either side of some finite value, then you have what's called a vertical asymptote at that value. Right? And that's really all we're doing for this video, right? Just describing with these arrows, what happens at the ends and what happens locally, what happens around some finite values where there may be some vertical asymptote. Okay. I guess the only major difference between this and previous videos is now you have this little minus sign, little plus sign for from the left, from below, and from the right or from above. Great. Alright. The next example I want to show you is the try it problem number 1 from the same section from the text. So let's take a look at that. So use arrow notation to describe the end behavior and local behavior for the reciprocal squared function. Now it's assumed that you know what that is. That's one of those toolkit functions, from earlier in this text that you should know, right? The reciprocal squared function, remember, is this. It's f of x or y equals, and then the reciprocal of x, but squared, right? 1 over x squared. And this is, again, one of those toolkit functions. You should know what this looks like. I'll draw a rough sketch of it over here. It's always a positive value, and you'll see that we'll end up having a horizontal asymptote on the x-axis. There's y equals 0. Y equals 0, the x-axis. That's going to be a horizontal asymptote. And then you're going to see also that the y-axis, or x equals 0, is going to be a vertical asymptote. And again, you should know what this looks like. You have 1, 1 over here, and as x values got smaller, the y values got bigger, and as x values got bigger, the y values got smaller. Something like that. Approaching the y-axis and approaching the x-axis without actually touching them. And then the same thing on the other side, always positive here. Something like this, but very symmetrical. This is actually a bad drawing, but should be more symmetrical than what I've drawn. Should be symmetrical about the y-axis. This is actually an even function. But we're seeing that, if I talk about end behavior, as x approaches infinity, as you go to the far right forever, see the value of the function is going toward 0. F of x is approaching 0. And same thing for the other side, right? As x goes to negative infinity, the value of the function is also approaching the x-axis, which is y equals 0. And either one of these tells me that this function f has a horizontal asymptote of y equals 0. Okay, and then the local stuff, is just basically where they're asymptotes vertically, or x-intercepts or whatnot. There'll be more stuff added to that, but right now we're just talking about vertical asymptotes, and that happens at x equals 0, right at the y-axis. You see, as x approaches 0, I'll start from the left side, right? A little minus sign, remember? As x approaches 0 from the left, the value of the function is going to infinity, right? Going up forever. F of x approaches positive infinity. And the same thing happens on the other side, right? As x approaches 0 from the right, the function's also going to infinity, right? The output. So as x approaches 0 from the right side, right, with a little plus sign, f of x also approaches infinity, right? And again, if this happens, if x is approaching some finite value from the left or the right, and the output's going to infinity or negative infinity, you would say that the function has a vertical asymptote there. So f has a vertical asymptote of x equals 0. And that's it. Again, the key there was, remembering what the reciprocal squared function looked like. Again, this is a rough drawing. It should be more symmetrical than what I've drawn, but it's got the general idea down. And that's all you need to be able to describe this end behavior and local behavior. Alright. And I just got one more example here. I'm hoping that seeing a few of these, helps you when you're using arrow notation yourself. I just want to do the very next try it problem in the text. Try it number 2. So you got another example to read if you want to try that one. Okay, here we got try it number 2. Sketch the graph and find the horizontal and vertical asymptotes of the reciprocal squared function that has been shifted right 3 units and down 4 units. So we just saw in try it number 1 the reciprocal squared function, but now they want us to shift it to the right 3 units and down 4 units. Now I'm hoping you remember function transformations, because that would look like this. Right, the original was just 1 over x squared, right, the reciprocal squared. If I'm shifting it to the right 3 units, it means I'm going to replace x with x minus 3, so 1 over the quantity x minus 3 squared, and then shifting it down 4 units, I'm going to take this rule here and then subtract 4 afterwards. So there's the reciprocal squared function, shifted to the right 3 and down 4. Now if you remember what the last graph looked like, that will help, right? If you remember what the original reciprocal squared function looked like. Because when you shift graphs around, the asymptotes move as well. So I'll bring that graph back, right, the one I drew of the reciprocal squared function. This is from try it number 1. If I move this graph right 3 and then down 4, everything moves. The asymptotes move as well. Moving right or left moves the vertical asymptotes, and then moving up and down moves the horizontal asymptotes. So instead of 0 and 0 being the asymptotes, y equals 0 and x equals 0, I'm moving it, right 3. So now x equals 3 is going to be the vertical asymptote. Put a little dashed line there. And then I'm moving it down 4 as well, right? And so instead of x equals 0, it's going to be x equals negative 4. There's going to be a horizontal y equals 0. Instead of y equals 0, it's going to be at y equals negative 4. And then the rest of the graph is the same look. I'd have 4, negative 3. I'll put some points in here. 4, negative 3 would be on the graph. And so would 2. 2, negative 3 would be on the graph. And then it's the same shape. I'm just trying to make it look more symmetrical about this line x equals 3 here. The same shape as the reciprocal squared function I drew earlier, but approaching, these asymptotes instead. Like that, something like that. I tried to make it look more symmetrical this time about x equals 3. But if you already knew, and you should have, right, the shape of the reciprocal squared function, I'm hoping your transformations are in your head, right? We did in previous videos in this particular text in previous sections talked about function transformations. So this shouldn't be too hard to do. And now we're seeing that all it asks us to do is identify asymptotes, but I'll still write all that behavior stuff down with the arrow notation. That's the whole point of this video. So let's talk about the end behavior first. I'm seeing that as x approaches infinity, we'll talk about going to the right forever. See, the value of the function is approaching negative 4. Right? It's not actually hitting the line, but it's approaching it. Right? It's getting closer to it. So f of x approaches, negative 4. Same thing for the left end. As x approaches negative infinity, the value of the function, the output, is also approaching negative 4. Okay? And then put either one of these tells me that the graph has a horizontal asymptote at y equals negative 4. And this is like part of the thing they wanted, right? They wanted you to identify the asymptotes. And then I'm seeing a vertical asymptote at, x equals 3. And again, we can describe that behavior though. So as x approaches 3 from the left, right, little minus sign above it, as x approaches 3 from the left side, you see the graph of the functions going up forever. So the value of the function is approaching infinity. And that tells me there's a vertical asymptote at x equals 3. And the same thing for the right side, right? As x approaches 3 from the right, right, with a little plus sign, so you approach 3 from the right side, the value of the function is going up forever again. Right? So f of x is again approaching infinity. And either one of these tells me that this function has a vertical asymptote at x equals 3. And that's what they wanted from us, right? To identify the asymptotes. And that's it. That's really it. Okay. So I'm hoping the use of arrow notation isn't too difficult, right? And you're just looking at a picture and pointing which way things are going, really. Where am I going on the x-axis? To the right's infinity, to the left's negative infinity. Am I approaching a specific value from the left? I use a little minus sign above it, or from the right, I use a little plus sign above it, right? And then where is the graph going? That's what f of x is doing, right? And I feel like this is pretty simple. Alright, so I'm hoping that watching me go through a few examples here also helps you, when you're asked to identify end behavior, local behavior, horizontal asymptotes, vertical asymptotes, using this arrow notation on your own. And thank you very much for watching.